So there are two things that I would like to try and do right now. Okay, so the thing that I just gave you to check that it has a first and second coordinate, you can distinguish the points and say which one comes first and which one comes second. This is the unordered pair, because the order in which x and y appear doesn't matter. But this is the ordered pair because there is a distinction between x and y. We can say which one is first. So this is, by definition, the ordered pair. This definition was given by Kuratowski somewhere in the 30s. He said, we need something, and he wrote this down. And this is the most elementary. You see other attempts, but they seem a little bit artificial. Again, this is unique by extensionality. So we have another function symbol with another property. We can simply say that this thing behaves like an ordered pair. This is our ordered pair from now on. And I'm using sharp brackets for that. Okay, what other axioms do we have? Well, axiom 5, again in Kuhnen's list, is union. Well, that we already talked about. Let me the union axiom has the same structure as the pairing axiom. It doesn't say that Z is the union of the family. It simply says that the union of X is a subset of Z. Comprehension allows you to define the union, because we take the separation, comprehension, separation. We take Z, we use the separation axiom on this formula here. All the U's that satisfy this, that is exactly the union. And then we prove that the union is unique. There is only one union, so we have another function symbol. And we're going to get way more function symbols all the time, because there are going to be tons of abbreviations running around in set theory. But that general theorem from first order logic tells us, fine, we don't get anything stronger. What we can prove with all those abbreviations, we could also have proven without them. Okay, let's get this out of the way. Now, so the unique and everything, and I'm not going to repeat that over and over again. I'm just going to say it, and you can check it all the time using extensionality. The next axiom that I want to discuss is number 6 in Kuhnen's list, and it's not from Zermelo. It's the one that Frenkel and Skolem discovered would be necessary. And since we have defined the ordered pair, let me introduce that axiom using can we prove that we can make the Cartesian product?
Do you need power set to do that?
We could use power set, but I want to do it another way now. That will be on the homework, by the way. The homework will appear at 4:45 this afternoon on the ELO. At least I hope so, that I put all the flags right so that it will appear. If it doesn't, let me know and I'll try to make it appear. Does it exist? Can we use it?
You need to say where the order pairs be.
You mean we want to use separation, for example? Is that what you mean?
Yeah.
From what?
We know where we can pick them from.
So, where? Well, if the set is finite, if x and y are, say, finite sets, well, as far as we can see, we can do this. Because we can simply write a very long formula that says, we have 10 elements in x, so we have u is equal to the first, u is equal to the second, or to the third, and v is equal to any one of the Google many elements of y. That's a very long formula, but can be done. Okay, but if they are infinite, although we don't know what infinite means yet, but suppose we just don't know what the nature of the set is, and we want to try and give a general way of showing that this exists, whether it's finite or not. Just we only know that there are sets, and we want to create that product. Now, like I said, here somebody mentioned the power set, and that's going to be on the homework, because that's a bit easier. So how do we do this? Can we use, say, the union axiom?
Because if we take just the union of x, right, doesn't that give us access to all the u's? No.
Well, we have, we fix an element of x, and we can do this. We fix u, and for every v, we can do this. Notice, this is completely unique because the ordered pair is unique and the singleton set is unique. So this is a function, actually. At least a function symbol, we can use that. Can we do this?
Not without
You need to-
replacement.
Yeah, what he said.
Yeah, not without replacement.
Not without replacement. Okay, so you gave it away. I'm working towards replacement, yes. That's what I'm going to pull out of the hat. Suppose this was a set. Then we can do this. And then we can create this product. Right? And then we could get the whole Cartesian product as the union of, say, the vertical lines. So we can create one vertical line as soon as we can create this set here. Now, everybody thinks, yes, of course this is a set, because it's just a copy of Y. A faithful copy of Y, because in this particular case it's even bijective with Y. Every V in Y corresponds to that particular ordered pair. It would be shocking if such a nice copy of the set Y would not be considered a set. Well, actually, Zermelo's axioms will not allow you to prove that that would be a set. Because you cannot, you can try a lot of things, but you cannot find an encompassing set where you can use separation on. Now this is an easy case. There are more complicated cases. Both Frankel and Skolem used something that we can only express when we have the power set axiom available, but I wanted to avoid that for today and talk about that. Well, you know the power set axiom already. I'm asking you to use it, at least in the homework, to create this. Think what this is a subset of if you have the power set axiom. And nobody tell anybody else yet. So what do we need? Well, we need something that tells us that this copy is a set. And that is axiom 6, replacement. And I will come back to Frankel's and Skolem's need for that as well. By the way, there is a link also on the ELO to this book. That's the only place where you can find Skolem's article, as far as I could find. So if you want to read what he did, it's an English translation of what he did at some talk at some Scandinavian Mathematical Congress. That's where he did the definite properties. He told the people we need replacement axiom, and he also showed in that article that set theory is relative, it has countable models. All in one speech, I would say. I've tried my best to find the original, I couldn't find it. But that one, it's on the archive.org site, the Wayback Machine, and you can borrow it. You have to become a member of that library, that's the only drawback. Or you can just Google for the PDF. But I didn't say that. Remember, I forgot to say something when I did the separation axiom. I said Y should not be free. And I'll tell you in a moment why that was the case for the separation axiom and also why it is the case for this axiom. Okay, and I'm going to introduce an abbreviation. we do this all the time. For every x in a set, something happens. And that's not a thing that I put in the list of symbols that we could use. It was not in one of the production rules of the well-formed formulas. But it's an abbreviation of this. And you can imagine what there is an x in u in x phi means. This is an easy abbreviation. It makes formulas a little bit shorter. Suppose you have a formula and you know that for every u in x, there is exactly one w such that this formula holds. Now you can write this down as a formula. For every v in y, there is exactly one ordered pair whose first coordinate is u and whose second coordinate is v. That is what this could express, for example. Suppose you have a formula that does that, then we have a copy and it is a set. Then we have we have a y such that for every u in x, there is something in y that does this trick. So in our case, we could find a set that contains all those ordered pairs. And then separation tells us we get exactly the set of those pairs. But okay, so two comments. Why should y not be free in this formula? Because then you get y defined in terms of itself. And the same thing happens with that comprehension thing. So then you say, well, something is in y if and only if it's related to y like that, while y is not even complete. And we don't want that. And the same thing here. We want to avoid defining y in terms of itself. And the other thing is, why did Kuhnen do the axioms with subsets rather than exact sets? Well, that's a little bit easier when you do model theory. It's a bit easier to prove that there is a bigger set that meets your requirements, and then comprehension will tell you that you have exactly the set that you need. But in some theoretical circumstances, just saying there is a bigger one is easier. It makes for shorter proofs. So this is what Axioms 6 says. If you have a copy, a partner for every member of your set, then those partners are part of a set as well. It doesn't say that for different u's we get different w's. In this particular case we do. But this could also be, there could be just one w that works for all the u's, for all I know. But never mind. This is the replacement axiom. And what I have just sketched here tells you that the replacement axiom proves that this product exists for every pair of sets. And then, of course, by comprehension and whatever, it's unique extensionality. And so we have another function symbol that gives us the Cartesian product of two sets all the time. And in fact, we'll keep on getting them. Okay, well, I have time for one more. So the reason that replacement was really needed, I'll come back to next, well, really, but the reason why Frankel and Skolem said it's needed, I'll come back to next week when we're talking about the power set axiom and a few other things. So I want to finish with axiom 7. And by the way, there is a reason why Kuhnen did it in this order, and when you look in Yech, the order is slightly different. Although you could say that Yech should have done this order as well, because in the model theory of set theory, you don't always have the power set axiom. But you do want your Cartesian product. Replacement axiom is good enough. And replacement holds in very many situations, as we shall see. Or you don't have the replacement axiom, you're like Zermelo, and you want your Cartesian product. Well, you can have that too, use the power set axiom and comprehension. But you'll have to think about that for your homework. Infinity axiom. So what was Zermelo's attempt? Zermelo's attempt was say, well, there is a set that contains the empty set, and with every A, it's singleton set. There's nothing wrong with that, except that it's a little bit cumbersome to play with, and that's why I put it on the homework. I'm going to talk to you about the easy bit, but if you understand the easy version and you understand what I talked about in the beginning, the homework should be doable. This is the set theoretic successor function. This is sort of like the minimum set that contains X and has X as an element. It's the smallest set that does that. So yeah, that's sort of successor-ish. This is it. This is the infinity axiom. And it's, okay, so in Kuhnen's book, you will find exactly this. In Yech's book, first he says it in words, and then he explains how you get it in formulas. I think you have it there in front of you, right?
You mean, yeah.
Yeah, but on a few pages further, he will go through all the axioms and actually explains what it means. Okay. The empty set is a member. It's like I said, this is Yech's existence theorem for sets, because he says there is a set with a certain property. Well, I put the symbol for the empty set here, but of course then there is a y in X that has the property that it's got no elements and everything. And then we know that it's the only one, blah, blah. So this is an abbreviation already. And it's closed under this mapping. Okay. We call X inductive in this case. And why? Well, because you can do induction on this kind of thing. Just like Zermelo said, it is the small, you can now take we can take such an X and we can then take the members of X that belong to every inductive set. This is legal by separation. So this is the smallest inductive set. So you could abbreviate that with IX or something like that. Now, what can we say about this thing? Well, the empty set is there. This is there because it's the union of the empty set and singleton the empty set. This is an N. And I'm going to stop here because somebody once calculated how that number of parentheses is growing. It's too bad. It grows quite quickly. So that's why I'm not going to write down the next one. Now, we tend to abbreviate this by 0, this by 1, this by 2, this by 3, and so on. I mean, if there is anything that should symbolize 0, it's the empty set. Don't you think? So in set theory, this is 0. This is 1. This is the prototypical thing with one element in it. And this is the prototypical thing with two elements in it, as far as we see what 2 means, and 3, and so on. So for all the members of N, we have this. We define plus 1 simply to be this. And this thing is our natural numbers. You can prove that it satisfies the basic Peano axioms and that you can define addition so that it actually satisfies all the axioms that Peano had a list this big, but in most of the books it's gotten a bit shorter. Well, you have to prove all this. And so if you have an inductive set, then I can find a smaller inductive set with a sort of desirable property, namely that every element is a successor, other than the 0, of course. So that's inductive, and that's a good thing to practice right now. So every element of N is either the 0 or it's the successor of something, which is something that is one of the Peano axioms, by the way. This is also inductive. The empty set is a subset of everything. Write it down formally. And of course, if X is a subset of A, then singleton X is a subset of A, and the union is a subset of A. Wait, what? Transitive? Maybe this is something that not everybody has seen. A transitive set is one such that every element is a subset. The element of relation is transitive, at least when X is the last one. It says if Y is an element of X and Z is an element of Y, then Z is an element of X. That's transitivity for the element of relation. Is the empty set transitive?
Yes.
There's nothing to check. If X is transitive, is the successor transitive?
Yes.
Yeah. If Y is a member of this, well, if it's a member of X, done. If it's a member of this, then it's X. Done. I think you need transitivity here, so the last time I did that exercise, all the members of X that are transitive and not a member of themselves. Yeah, you need transitivity there. Nothing that we have done so far prohibits this. Let's use a double negation here. It's still not illegal to have a thing that is a member of itself. But if we're doing this thing, we're building the natural numbers. And what do we want with the natural numbers? We don't want a natural number to be strictly smaller than itself. And what is going to be the nice thing about the natural numbers? The element of relation is the linear order. We don't have to define a linear order of that set. We get it for free. It's the element of relation itself. Pretty good, eh? Now, I mean, there is a reason that you would want to do this. You don't want to introduce anything new that is not really necessary. And with this, and with the ordinal numbers that we'll also talk about next time, this is simply going to be the order relation. What else? Well, you can now, I think, I think you can now, or maybe the order is slightly different, but you can now prove that the ordering, the element of ordering, is linear. And it's only one of the three that you get. Because of this and the transitivity, you don't get two of those at the same time. You only get one. So the element of is a linear order on n. Well, the next step is to show that it's a linear order on n, and then you have to show that any two elements live in one element of n. But I think you have to go, there is a moment when you have to talk about the natural numbers themselves, and I think this is it. Okay, let's leave. What other thing can you prove? Well, you look at this order, you can show that every subset of X, you take the X's every subset of X has a minimal element with respect to the element of relation. Well-founded is the word that we'll be using for that later on. So every subset of X has minimal elements, and when you combine that with the linear order that you get from this, it shows that if you take a member of N and you take a subset of that, then it has a minimum.
Don't you mean V is not included in U?
You're right. Thanks. And from that, you can prove that this order is a well order of the natural numbers. Take a non-empty subset of N, take a member of it, and look below it to look for the minimum of your set. And you can, okay, so I went on a bit too long, but those are the things you can prove these step by step, and then in this way, you show that those things actually are the natural numbers. And I've stolen these things from chapter 1 of Yech. It's the exercises of the first chapter. You will see that. They're probably in a better order than what I just wrote down.
I think there's still something problematic
I
there.
think it's Z, it's not U.
Pardon?
The V doesn't belong to Z. It was corrected.
Yeah, V is not in Z. Right.
That's right.
We'll get there eventually. There's only finitely many letters we have to change until it's correct. And if you all help, then we'll get there. Okay, I think that's it that I wanted to talk about. So next time we'll add, I think all we need is the power set axiom, and we'll talk about the axiom of choice a bit. Pardon? Maybe later.
You don't need foundation.
Well, we need foundation when we start to talk about the models. We can do without it for quite a long time.